All right, good afternoon, everyone. Good afternoon. So today is our final class on this unsteady combustion processes. So we're going to shift gears today, and we're going to move from thinking about maybe some transient combustion physics problems. You know, we've talked about, we started first talking about just the general problem of flame aerodynamics, the interactions of flames with the flow, and sort of a motivating practical problem that we talked about in that context was flashback. And then yesterday we talked about edge flames and flame stretch, and sort of a motivating practical problem that we returned to there was the problem of blow-off or flame stabilization. So today what we're going to talk about is just generally the propagation of disturbances in reacting flow fields, and we're going to talk first relatively generically about what disturbances look like, and I'm going to introduce to you a canonical decomposition of disturbances in reacting flows, and but we'll also spend a little bit of time talking about thermoacoustics. I think there's probably a good third of you, if I remember right, in this room are working on that problem in some way or the other. So we'll talk about thermoacoustics, and we'll talk about thermoacoustics, but the flame will be sort of a black box. We're just going to treat it, how the flame responds to disturbances, in a very generic way. And then we'll spend the last third of the class talking more specifically about the detailed physical processes when you disturb a premixed flame or you disturb a non-premixed flame, what actually happens and why the flame moves around and why the heat release changes with time. So that's the plan, and since it's day 3, I thought I would kick things off by showing you all a couple fun little videos just to kind of make life interesting. But anyway, just to bring it, I should have put this slide up here earlier. So we're talking about disturbance, propagation, and generation reacting flows, and then we'll finish by talking about how flames respond to these disturbances. In particular, we're going to talk about how flames respond to harmonic disturbances. And this is kind of an interesting topic because, as I'll show you, everyone in here who's taken a turbulent combustion class has thought about how flames respond to disturbances. In that case, you've been looking at how the time-averaged burning rate or time-averaged flame position changes when the flame is disturbed basically by Navier-Stokes turbulence. That's in essence the turbulent combustion problem, right? It's what's the response of the time-averaged burning rate to amplitude of turbulence intensity. But what I'll show you is when you harmonically excite a flame, which is also a very important problem, the way the flame responds is quite different than if you excite it with stochastic disturbances. In particular, some of you may remember there's this thing called the ergodic. Well, if you have an ergodic time series, time averages and ensemble averages are equivalent. So if you take a time average, so if you average in time, or you repeat an experiment in times, and you average at a given time, those in trials, you get the same answer, which is true for turbulent disturbances. In contrast, when you have a harmonic disturbance, those are not ergodic. So time averages and ensemble averages aren't the same. So that has some pretty significant influences on how the flame responds to harmonic disturbances. So let's get started here. And we're going to start with an introduction. And like I said, I'm going to just kind of motivate some of the problems that we're going to be looking at here. And so one of the big motivations is this problem of thermoacoustic oscillations or combustion instabilities. And what I've sort of illustrated it schematically here. And the idea is that if you take a flame, which is a source of heat release, when you disturb that source of heat release, the flame responds. It doesn't just sit there, it responds. And so you get, it moves around, you get disturbances in how reactants are converted into products and so forth. And then when you take that heat release and you place it inside of an environment which gives you feedback, namely a combustor, you create the possibility to close the loop. So if this is always happening, the bottom half of this loop, and then when you place the flame inside of a resonator, the top happens. And you may remember on Monday I said, what's the difference between a premixed and a non-premixed combustor? Well, a combustor used in premixed applications is an organ pipe, whereas the combustor used for non-premixed applications is a muffler. And so the degree of this feedback changes dramatically, and that's one of the reasons why, as combustion designs have continuously evolved towards more and more pre-mixed, and you need all that air in order to get the low equivalence ratios for low NOx. What has inadvertently happened is that combustion designs have lost all their acoustic damping. They've gone from being mufflers to being organ pipes. But what happens is this feedback loop, it occurs at a very specific frequency. So the feedback time scale is usually moderated by the natural acoustic time scales of the system. So the flame makes sound propagates away, hits the end of the combustor, comes back, and then you get this feedback. And so that, and what that does is, so if you have a really long combustor, you'll have low frequency oscillations. If you have a really small combustor, you'll have high frequency oscillations. So for example, an application might be a really big refinery. So go to Texas, there's these massive refineries, they might be hundreds of feet long. You can have oscillations of 1 hertz, thermoacoustic oscillations of 1 hertz, which is way below what your ear can hear, but it does all these weird things to your organs, in your inner ear. Whereas if you're talking about a tiny little, maybe an instant water heater, you can have thousands of hertz oscillations. So I keep forgetting I have these slides. So this is this is something you can all try tonight, which is resonant modes. As I mentioned, if you have something really long, you have low frequency modes. If it's short, you have higher frequency modes. In the same way, any type of combustion system doesn't have a acoustic mode. It has multiple acoustic modes. You can have axial modes. You can have modes going back and forth in the axial direction. You can have modes bounce if it's a can system. So if it's a round combustor, you can have modes kind of bouncing around transversely or side to side. If it's an annular combustion chamber, so if you have a big annulus like an aircraft engine, you can have acoustic waves spinning around the annulus. Or the annulus, you could also have waves bouncing around radially. So these all happen. And so if you've ever blown over a milk jug or you've ever blown over a beer bottle, you'll hear what's called the Helmholtz mode. That's the lowest frequency mode of a device that has a volume connected to a constriction. So basically, this is what's called a Helmholtz resonator, when you have a volume connected to a restriction or a neck, which is why a milk jug or a beer bottle do this. But this is a slide that shows what happens if you actually take a Fourier transform of somebody blowing over a beer bottle. This is what you get. And so this is frequency. And so you can see that there's these really narrow band peaks, which correspond to resonant acoustic modes of this beer bottle. You'll see one at 190 hertz, that's that Helmholtz mode. You'll see one at 1225 and 1775. These correspond to axial modes, bouncing around back and forth. Then you'll also see some pretty high frequency modes, 3700 hertz and 10,600 hertz. These are modes bouncing around side to side. Now, the reason the transverse modes have such higher frequency than the axial modes is because this dimension, at least of a beer bottle, this dimension is shorter than that dimension. So if you think about it, a natural acoustic mode is roughly, it's on the order of the amount of time it takes for an acoustic disturbance to make a round trip. So you think about a sound wave starts here, it goes here, it reflects off the open end, and it comes back. All right? Now, if the tube is longer, it takes a longer amount of time, and the frequency is 1 over the period. Now, if the sound wave is bouncing side to side, it takes less time for it to bounce side to side, which is why it's a higher frequency mode. Now, we'll get into this a little bit more later, but one of the key problems here, let's see if I can get this video to work. We're going to spend a whole hour talking about this issue. But one of the key issues here is that flames are sensitive to disturbances, all right? If you disturb a flame, it will oscillate. So this is a really nice video that was taken by Sebastian Candel at École Centrale. And super simple flame, not like anything encountered in applications, but the reason I really like this is it just, all the physics is here, minus turbulence. And what you have here is a Bunsen tube, okay? So this is just a simple Bunsen flame. If there weren't any oscillations, here's your Bunsen tube. If there weren't any oscillations, you just see a nice little Bunsen flame like we were talking about when we talked about stretch flames. That's what you'd see. And what they did was they took a speaker and they put a T on the bottom and they generated modulations in So that what's happening is the air flow rate, the reactant flow rate coming out of the tube is not constant. It's oscillating in time. So you have a modulation in the reactant flow rate into the system. And what you're looking at here is a Schlieren image. So this right here, this edge right here Schlieren is sensitive to density contrast. So what you're looking at is you got reactants here and you got products on the other side of the flame. So you see the sharp gradient, which is associated with the temperature jump across the flame. What's going on out here? What do you think this is? Nope, there's no diffusion flame. This is a lean flame, but that's a good thought. It's a hint, right? There's a big density change that's happening here, and there's a density change happening here. This is just simply the combustion products meeting the ambient. So you got cold, right? This is in a, if I just take a flame and I put it in here, I got cold reactants coming out. I got an ambient, and then I got this hot products in between. So I have two density interfaces. But so a couple things you can see happening. First of all, you see the whole flame bouncing around. And what's interesting about it is you see these wrinkles, which actually seem to be initiated right at the point where the flame stabilizes. And then you can watch those wrinkles, they convect downstream. So you watch them, and they convect downstream. And then you watch them, and they convect downstream. And if you watch the part that's convex to the reactants, you'll watch that convect downstream. So clearly the flame position is oscillating. What's also, you can tell by looking at this outer edge, if you think about it, this outer edge is the boundary of where the hot products are. And because this boundary is oscillating, that's telling you that the volume flow rate coming out of the flame is oscillating in time. Okay? So remember, flames are sources of volume flow rate. Mass is conserved, volume flow rate is not. So flames are sources of volume flow rate, but because what this is telling you is the volume flow rate coming out of the flame, though, although not only is it a source, but it's a source of unsteady volume flow rate. And that's what you can clearly see from this outer edge. In other words, the rate at which reactants are getting converted into products is oscillating in time. It's not just that the flame position is oscillating. Because it's possible, you could potentially think of a scenario where the flame is moving, but the rate of heat release isn't changing. But what this is showing you is, yes, the flame is moving, that's obvious there, but this outer interface is telling you that the rate of heat release is oscillating. And again, the argument is, it's telling you that the volume flow rate is oscillating, which tells you that the rate which reactants are converted to products is oscillating, which is basically multiply that by delta H and you got heat release. Okay, so the flame's moving around and you're getting oscillations in heat release. Now, why do you think flames make sound? Anybody have any ideas? I don't know if anybody has an acoustics class, has ever taken an acoustics class. Yes, sir. Yeah, exactly. And what kind of sound source do we call that? There's a name for that kind of sound source. Monopole. A monopole. It's called an acoustic monopole. Flames are acoustic monopoles, which, by the way, is the most efficient mechanism for radiating sound. If you ever take an acoustics class, there are things called monopoles, there's things called dipoles, there's things called quadrupoles. So, like jet noise, when you have a high-speed jet, it makes noise. It turns out it's a quadrupole. So jet noise is a relatively inefficient converter of kinetic mechanical energy into sound. Flames are super efficient because they're monopoles. And the easiest way to think about a flame is if you look at that speaker up there, you'll notice that, what is a speaker? A speaker just consists of a cone, right? Just think a piece of paper, and it's just oscillating back and forth. There's an electromechanical driver shaking it back and forth. Now, if I just had an electromechanical driver shaking that disc back and forth, it wouldn't make much sound at all. That speaker would be lousy. But what it does is it sticks that thing inside of a case. So in other words, if I, sorry. Can you still hear me? Does that still work? Okay, sorry about that. So in other words, I have this diaphragm which is shaking back and forth, all right? That's how that thing is making sound. But what they do is you put it inside of a case. I don't have other colors, so let's see. Maybe I'll just go like that. This thing shakes back and forth. So what's happening is it's a volume source. So the volume of that box is changing in time. It's pushing air out of the way. That is what we call a monopole. If I took the speaker, if I took the case away, it would be what's called a dipole. A dipole is a source of force. But a monopole is a source of volume. So remember, flames are sources of volume flow rate. And because the volume flow rate is oscillating, you're getting an unsteady creation of volume by the flame, which is a monopole. Very efficient sound generator. So flames will oftentimes dominate the sound emission by a flow unless the flow starts to get an appreciable Mach number. Okay. Now, what also makes life really kind of interesting is flames are sensitive to sound, but if you have a combustion system where the flow is subsonic, subsonic means the flow is going with a velocity less than the speed of sound, right? So if I make sound, it's going everywhere. Everywhere. It's going upstream, it's going downstream. If your fuel supply system is not choked, it's going into your fuel supply system. So the pressure drop across your fuel injection system is oscillating in time. It's going everywhere. And so the whole combustor system is actually sensitive. This is kind of a fun little video. It's a good after lunch wake up video that demonstrates this point.
Let's do a classic physics experiment called the Reubens tube. Now, I really want to bring it down, but it involves open flames, and some people have issues with open flames. So, what we have here is a length of PVC pipe, has about 100 or so holes drilled at half-inch increments, got some foil tape to keep it from melting. On this side, we've got a 2-inch speaker matching the diameter of this 2-inch tube. On that side, we've got some lab tubing leading to some propane. So let's fire it up and see what it does. All right, as you can see, we got some nice standing flames, a little bit of oscillation from the vibrations in the hose. Let's throw some sound in there and see what happens. Let's start with a 449 hertz frequency. As you can see, this sets up a standing wave, and we can see, well, the emerging sine curve that represents sound. What happens here is we're having the sound compressing here and not compressing here. The lower pressure here allows more gas to escape into the atmosphere, shaping the sound curve. Now, if we change the frequency, we can see each time we set up a standing wave, we get that sine curve. Higher the frequency, the more waves. Now let's throw some music at this. How about some Dave Brubeck? Now we have real life sound visualization with fire. Isn't terribly energetic, so let's try something a little more energetic.
I've never been able to figure out what's happening over here.
Now that's some good physics. I'm going to turn off the gas.
All right. Anyway, that is called a Reubens tube. By the way, if you go to YouTube, there must be 15 or 20 of these demos. And I was talking to somebody yesterday. There's even a two-dimensional version of one. You can see the flames bouncing in 2 dimensions. And you said you did this in physics class, sir. Is that correct?
Yeah, I had to teach about a 40-foot long 6-inch tube.
Yeah. See, we don't do that stuff anymore. We're not allowed. This darn fire marshals. 40-foot long 6-inch tube. That's a lot of oomph. If yeah, you could DDT in that almost. Okay. Cool. Okay, so that's a Reubens tube. Actually, let me just show you one more video while we're on a roll. It turns out that combustion, or these combustion instabilities, it's part of there's a broader phenomenon in physics called thermoacoustics. And the basic idea is that when you have sound interacting with temperature gradients, is that you can have spontaneous sound generation. So for example, when you have a cryogenic piping system, if you have really abrupt temperature oscillations, imagine you have a packet of fluid. If it's bouncing around, it bounces between a region of low and high temperature. It's going to expand, contract, expand, contract, and that can actually make sound. And so you can actually get spontaneous sound generation. You know, you'd think your piping system is bewitched. It just starts hooting at you or screeching at you or something like that, and it's due to thermoacoustic oscillations. In the same way, you can actually turn the phenomenon around, and if you have a driver, so you have an acoustic driver, you can actually pump heat like a refrigerator. So the refrigerator on the space shuttle, or that was on the space shuttle, was actually a thermoacoustic. And the reason is a very, very small number of moving parts relative to the refrigerator that you may have in your house or apartment. So a lot fewer failure mechanisms. So actually, this video didn't work. Dang. I don't know why it's not working. Let me try finding an, I don't know if it got corrupted. Where'd I put the blooming thing? Okay, bummer. Try this one.
This is a Rijeka Tube, and it's one of my favourite physics demonstrations. At the point marked in the tube, there's a small metal gauze. The demonstration involves heating the gauze with a Bunsen for a few seconds. When the Bunsen is removed...
Okay, so just to get you oriented, this is a piece of pipe. It's open, all right? So open on one end, open the other. So just took a piece of copper pipe, and what he wants to do is he wants to make it hot about a quarter of the way up. So the way he's going to make it hot is that he put in a really fine sort of piece of metal mesh that's there, and so when he puts this Bunsen flame underneath it, it's going to heat that metal mesh up. So when he removes the Bunsen flame, then what it'll have is an open piece of pipe with something hot right there. Okay, so there's strong temperature gradient. So there's going to be a convection current. So as you can imagine, it's going to be cold down here, hot up here. So there's going to be this big temperature gradient. But there's no combustion in this experiment. As soon as he removes the Bunsen flame, the combustion, it's just used as a heat source. If you go to YouTube, look this up on YouTube, and you look up Rijeka Tube, you'll see examples where if you use electrical heating or something like that. But anyway, so.
Moved, the tube sings at its resonant frequency. The resonance does not occur if the tube is tipped on its side, but it does return if the tube is placed back vertical. The resonance also does not occur if the tube is placed upside down. The explanation as to how it makes the sound encompasses a wide variety of physics. The tube was invented by the Dutch physicist Petrus Rijeka, who died at the end of the 19th century. If you want to try and puzzle out how it makes a sound, then pause the video now. The Bunsen burner heats up the gauze fairly quickly, which becomes red hot. A convection current of warm air rises up the tube to begin with, but it will soon subside once the Bunsen is removed. Air in the vicinity of the red gauze has heated up. Note that the centre of the tube is above the position of the gauze. The region of hot air causes the pressure to increase at this point, which forces air out of both ends of the tube. This is essentially a longitudinal pressure wave. When it reaches the open ends of the tube, it partially reflects back inside the tube. Now colder air has moved upwards past the red-hot gauze. This air is colder because it's been below the gauze, and hot air tends to rise due to convection. The air particles that have just risen past the hot gauze are heated, and so the pressure rise again. This provides the driving force for the resonance. The air is forced out of the tube once more, and then it reflects, and so the cycle repeats. Note, of course, that this animation is rather simplified.
I'll just stop that there. But that gives you the idea of, so it's pretty wild stuff. So you just take a tube, make it hot, a quarter of the way up, and the thing will just oscillate on its own. It's self-excited. You get a spontaneous oscillation. Okay, so that kind of sets it up, and I'll just note that this issue, combustion instabilities, it's a significant problem in practical combustion devices. And many of you are going to get your PhDs, it sounds like, working on this problem. I've worked on it quite a bit. Professor Yetter's worked on it quite a bit. Lots of people have worked on it. A lot of the initial work was actually done here at Princeton. And like I said, it's basically you're taking a flame that's sensitive to disturbances and putting it inside of a resonator. So pretty much any kind of high performance propulsion system or most modern low emission systems, you deal with instabilities in one way or the other. So for example, the F1 engine, which was the largest thrust engine the US ever flew, that was used on the Saturn V, big engine. And it had enormous combustion instability problems. They did 3,200 full-scale tests on that thing, and over 2,000 of those were basically trial and error tests where they were monkeying around with fuel injector patterns or adding baffles or things like that to eliminate oscillations. So this is actually, this is an example of what I mean by baffles. That's from this reference. But what you have is the injector plate of a rocket is just a really fancy shower head, right? It's a shower head that blows out oxygen in some fuel. And so the flame is going to be sitting some distance off that injector face. But what happens is when you have these acoustic instabilities, in many cases in rockets, they're transverse oscillations. So they're going side to side, and they're modulating how the fuel and the oxidizer are mixing. They're modulating the flame. And so the idea is if you'd like to keep these acoustic oscillations away from sort of that critical near injector region. So they simply would put these things you're seeing here actually intrude into the flow. They might stick out this far. It's a little bit hard to visualize. Just think of that. You have this flat plate with all these holes in it, and then wherever you see this stuff, this is sticking out into the flow a couple inches. And what that does then is it disrupts the acoustic motions near the injector face. As you might imagine, these things like to burn off, and so they only have a certain amount of life on them. Okay, this is just a couple other examples, and I'll skip over that. But so anyway, that just kind of sets up this whole some of the things that we're going to talk about for the rest of the day. All right, now I want to now move into, now that I've hopefully woken you all up, I want to move into a more theoretical topic. And I want to talk about decomposition of disturbances into fundamental disturbance modes. And I have a lot more material in these slides than I have time to present, so don't get stressed out if I'm jumping over stuff. But basically, I decided to put extra stuff in here in case someone had a question, so I could just go into more detail on it. But the basic idea is, you don't need to do this, so I'm going to jump ahead. Don't jump ahead. I'm adding a slide. I'm adding a new slide here on the fly. Where'd that slide go? And I'm going to stick in a box. Whoops. Don't let me hit save. Okay. What I'm going to show you is that when you're making measurements or when you're doing a calculation, you have these physical variables, right? Some of them are thermodynamic, some of them are fluid mechanics. So for example, you have the pressure, you have the velocity, you have the density, you have the temperature, and then maybe these slightly more well, vorticity is pretty obvious what vorticity is. Entropy is a little bit more fuzzy what it is in terms of what you would measure. But anyway, so you have these quantities. But what I want to show you here is these are actually when you have disturbances in these quantities. All this stuff is going to be oscillating. These are all manifestations of three fundamental canonical disturbance modes, which I'm going to call the entropy mode, the acoustic mode, and the vortical mode. All right. So imagine I have these three fundamental disturbance modes, which you can't actually, let's just say you can't actually see those, or it might be very difficult to directly measure those, but I can measure their manifestations. So in other words, what I'll show you is that the pressure, velocity, density, temperature, and vorticity and entropy, those are actually manifestations of, more fundamentally, an acoustic disturbance, an entropy disturbance, and a vorticity disturbance. All right? So that's basically what I'm going to talk about for the next 20 minutes, is this canonical decomposition. And it turns out that you might say, well, why this stuff is really intuitive and I understand it, and this is how the Navier-Stokes equations and the energy equation is framed. Why do you got to do this to me? And the reason is that, in fact, it lends a whole lot of insight. And I'm going to actually show you an example from real data, measurements in an unstable combustor, where if you're just looking at the data, you're like, I have no idea what's going on. But then once you look at it again, you'll say, oh, hold on. I'm going to show you velocity data, and you say, you know what I'm actually measuring is I'm looking at the superposition of an acoustic disturbance and a vortical disturbance. So what I'm measuring the velocity, but what's really happening is I have an acoustic and a vortical disturbance. So what I'm looking at is the superposition of those two, and then the blinders come off, and then it's super obvious what's happening. So let me hit Control Z. So that's just kind of I'm telling you what I'm going to say, and now I'm going to say it, okay? And then I'll tell you what I said. So in order to introduce this concept, I'm going to make a bunch of assumptions initially to get things started off, right? And then I'll talk about what happens when we relax those assumptions. And the first major assumption is I want to think about what happens when I have very small amplitude disturbances in a uniform inviscid flow, all right? So why do I want small amplitude disturbances? Because I want to linearize the Navier-Stokes and the energy equation, okay? I want to get rid of all those nasty nonlinear terms. Uniform inviscid flows, I'll explain what that means a little bit later. So what I'm going to do is I'm going to assume I have a homogeneous background flow. And by homogeneous, what I'm going to mean is spatially uniform density, spatially uniform velocity, spatially uniform temperature, spatially uniform pressure. And then what I want to do is I want to look at how disturbances in pressure, velocity, density, temperature propagate along that background. And you might say, well, hold on, we're doing combustion here. Why is it at all interesting to think about what happens when you have spatially uniform density? And what I'll tell you is that where you have changes in density, that introduces some new effects. But, well, tell you what, I'll get to that later. But just bear with me. Okay, and so what we're going to do then is we're going to take every variable and we're going to decompose it into a sum of a base and a fluctuating component. How many of you have done linearization, are familiar with linearization of the equations? Okay, I'm just going to go really fast then. So for example, the pressure, it's a function of space and time, and it's going to equal P naught, so that's the base state. And notice P naught is not a function of x by assumption, because I said I'm going to assume uniform. When I relax this assumption later, you'll see what happens. Plus a disturbance, so the naught denotes sort of the nominal field. The subscript 1 denotes a small amplitude disturbance. And so therefore, by assumption, P1 is going to be much, much less than P naught because I want to linearize. The density, same thing, rho 1 plus rho naught plus rho 1, the velocity U naught plus U1, et cetera, et cetera. And then what I'm going to do is I'm just going to jump over these next slides, and you can just take my word for it. If you juggle around the continuity, momentum, and energy equation, subject to those assumptions, you actually end up with these three disturbance equations, and the vorticity, the acoustic, and the entropy equation. So it just turns out that the linearized Navier-Stokes and energy equation just like to fall out and form these three equations. And so the vorticity equation, you will recognize this equation. This is a sourceless equation. It's actually, all these equations are sourceless, right? The right-hand side is 0, 0, 0. And in essence, what's going to happen when I start relaxing these assumptions about, I'm going to start adding sources on the right-hand side. But for now, these are sourceless equations. So what does this describe? Somebody give me a physical interpretation of this equation. Oh, I didn't tell you what D naught means. jumped over that slide. It's the substantial derivative, but it's a special substantial derivative. So it's the substantial derivative, but it's not u dot grad. So it's d by dt plus u naught dot grad. So it's the convection. It describes the time derivative moving in a frame of the nominal mean velocity u naught. Okay. So in other words, so d naught by dt, that just says what that is d naught by dt of omega 1. Omega is the vorticity, by the way. I can't remember if I defined that. So it says if I'm moving at a speed of u naught, if I'm moving at a speed of u naught, what's happening to the unsteady vorticity? So omega is the vorticity, the subscript 1 is the disturbance. So with that as a background, what is this equation physically saying? Well, I just sort of just said it. It says if I'm moving at a speed of u if I'm moving with the average flow, there is no change in vorticity, right? So if I'm looking at if I have an Eulerian reference point and I'm sitting there, the vorticity could be oscillating, right? I could see oscillations in vorticity, basically little vortices convecting past me. But if I'm moving with the flow, those vortices are frozen, all right? And so in other words, I don't have stretching and bending terms or diffusion terms. I've neglected all of those by the assumption. So it says that in a reference frame moving with the velocity, the vorticity disturbance, the vorticity is constant. What it also says, though, is that you have that these vortical disturbances move with the flow. All right. Entropy equation. Let's just jump down there. This says the same thing with respect to the entropy. So if I'm moving with the flow and I had an entropy probe, I would measure constant entropy. It wouldn't be changing in time. Whereas if I was at a fixed point and I had my entropy probe, I could potentially see oscillations in entropy. And then this equation right here. How many of you have seen the wave equation before? Okay, so you'll recognize this. It looks like a wave equation, but there's this substantial derivative. This is what's called the convective wave equation. It's the wave equation in the presence of mean flow. If there was no average flow, this would just be partial squared of P1 by partial squared of time squared. It turns out if the Mach number is low, the convection terms don't matter. So you can see the acoustic disturbance is a totally, vorticity and entropy satisfy the same kind of equation. The acoustics is a different equation. So this is first order in time, first order in space. This is second order in space, second order in time. And this describes wave propagation. All right? Okay, so that's just kind of a quick, the Navier-Stokes and energy equation naturally like to arrange themselves in this way. It's a nice simple way to do it. Now what I want to do is I want to say, let's take all these observables, pressure, velocity, density, and in fact, I don't like the way I did my notes, so do me a favor and write something a little different. Because thinking about the canonical decomposition of the entropy and vorticity is a little bit confusing at first. So write rho 1, P1, T1, U1, okay? What I'm going to do now is, sort of motivated by this idea, is I'm going to say, let's assume that the density fluctuation is itself composed of a superposition of these three canonical modes, right? So I'm going to say rho 1 S plus rho 1, forgot what I used, lambda plus rho 1 omega. Okay? So in other words, I'm going back, I am going to assume I have these canonical disturbances, which I don't have access to, which I may not be able to directly see, vorticity, entropy, and acoustic. But the density fluctuation, it's the superposition of those theories. Same with the pressure, and you can just write this out, etc. And it turns out you could say the same thing about the vorticity and about the entropy. That is a superposition of the modes. But this is a little bit more, if you're not used to this concept, this is a little bit harder to get your arm around. But I'll come back to that in a minute. Okay, so for example, P1 omega, this is the pressure fluctuations induced by the vorticity mode. All right? Or rho 1 S, that's the density fluctuation induced by the entropy mode. That's the physical meaning of that. Okay? Now, because these equations are linear, I can just take these substitutions, I can just drop them into those equations, or I could drop them into any of the other linearized equations that I jumped over, the linearized continuity, momentum, and energy equation. And I can decompose them into subsystems for each sets of equations. And I'm going to skip over all the details, and I'm just going to give you the answer. By the way, all of this stuff comes straight out of there's a very classic paper by B.T. Chu and Leslie Kvasny, who were also trying to make sense of measurements in a supersonic flow, actually, which is where this idea came from. And I have the references in my book. And by the way, I'm coming straight out of everything I'm talking about here. If you want to see more, does anybody, I think it's chapter 2 or 1. Is it chapter 2? Chapter 1, okay. Chapter 1 or 2, one of the two, I forgot. But it's chapter 1. Okay, this is all straight out of chapter 1 where I go into more detail on it. But I'm just going to give you the answer and say, okay, I have this vorticity mode. How does it manifest it in these observables? All right, let's start down here. So P1 omega equals 0. What does that mean physically? Somebody tell me what that means physically. Yep. So the vorticity mode induces no pressure fluctuation. The vorticity mode induces no entropy fluctuation. The vorticity mode induces no temperature fluctuation. The vorticity mode induces no density fluctuation. Basically, what this is saying is that the vorticity to first order is not modulating your thermodynamic variables. It's an incompressible disturbance, in other words. You have an incompressible disturbance, and it's not going to be changing your entropy or temperature or density. But what it does do is it manifests itself in oscillations in the velocity, right? And so what's happening then is vorticity and the induced velocity fluctuations, they're convected by the mean flow, but they induce no fluctuations in pressure, entropy, temperature, density, or dilatation. Actually, I didn't have an equation for dilatation. By dilatation, I mean del dot V. So del dot U1 is 0. So del dot U1 equals 0. Del cross U1 is non-zero for the entropy mode. So it's rotational but incompressible. Now let me ask you a quick question. This is an experiment you can all do. In fact, there's a ton of experiments in the literature where people will generate a vortex and they'll put a microphone in the path of the vortex and they'll measure a pressure fluctuation. In fact, people have suggested you can use this as a method for flow diagnostics, is use the pressure fluctuation. This equation says there's no pressure fluctuation induced by a vortex. So how do I reconcile those two observations? Well, in general, you're right. But what this equation says is P1 omega is 0. So what this is saying is there is no fluctuation in pressure, even as the velocity is oscillating. Nope, this is a fluctuation. Keep thinking. What's going on? Well, what this says is the vorticity oscillation generates no pressure fluctuation.
But it does.
So that's why I'm asking why. What's going on? Reconcile the two for me.
Because you have neglected viscosity.
I could, let's see.
Because in the moderate layer, you have
If I included viscosity in this analysis, it wouldn't change that answer. It would. What that would do is it would make this term non-zero. The viscosity would give me entropy fluctuations. It's not due to viscosity. But you're on the right track. What else have I'm neglecting stuff. I'm making simplifications. What was that? Yeah? So what have I done? What have I neglected? I assumed linearity, okay? So vortical disturbances excite pressure fluctuations at second order. So think about the Navier-Stokes equations. You got that that whole convection term, which gives you turbulence, right? That's a second order term. So you're right. Vorticity does excite pressure, but what that means is if I have a vortical disturbance of amplitude epsilon, the pressure disturbance is of order epsilon squared. So if I'm neglecting order epsilon squared terms, they don't show up in a linear analysis. So that's the answer to that. So keep that. It's important to keep that straight. Same thing is going to happen with these other disturbances. So the assumption of linearity is key here. Okay, so that's the vorticity mode. Now acoustics, so oscillations associated with the acoustic mode. So let's look at this one. What this says is the vorticity fluctuation induced by the acoustic mode is 0. So what does that mean? And while we're at it, let's just do this one. The entropy fluctuation induced by the acoustic mode is 0. Well, what it's saying is that let's assume I go back to my assumptions. I have a uniform background flow, and I introduce a sound wave. All right, I have small amplitude sound wave, and it goes zinging by. What this says is that sound wave is not going to excite any vorticity, and it's not going to excite any entropy. That's what that says. Okay. Now, what it also shows is, let's jump down to this one. It says that the density, the pressure, and the temperature are locally and algebraically related through their isentropic relationships. If you're probably used to seeing the full nonlinear form of isentropic relations, like pressure is equal to a constant times rho to the gamma. But if you linearize that, so if you assume pressure disturbance and density disturbances are small, you would actually end up with this, is that the density fluctuation associated with the acoustic mode is equal to the pressure fluctuation divided by c squared. And the same thing with the temperature. Now, locally and algebraically related means that if I know the pressure at a given point, I also know the temperature, and I also know the temperature by just through these algebraic relationships. And the reason I emphasize that is because it's not so for the velocity. Now, this is my equation that relates velocity and pressure. And you can see what it says is that the substantial derivative of the velocity is equal to the negative of the gradient of the pressure. So this looks a lot, you can see this comes straight out of the momentum equation. What this tells me then is that the time variation of the velocity in a coordinate system moving with the flow is equal to the pressure gradient. So the velocity and the pressure are not algebraically related or even locally related. Rather, what this says is this is the acceleration, right? The acceleration is related to the pressure gradient. All right, so that is the acoustic mode. And then the entropy mode looks like this. That P1s equals omega 1s equals U1s. So what that says is that the entropy disturbance excites no fluctuation in pressure, vorticity, or velocity, but the density, the entropy, and the temperature are oscillating due to the entropy mode. So let's summarize. Let's make a couple comments here. And we're going to come back to this because I know I'm feeding you from the fire hose. But what this says is that in a homogeneous uniform flow, first of all, these three disturbance modes propagate independently in the linear approximation. So for example, if I have a uniform flow and I have a vortex, an infinitesimal vortex generator and an infinitesimal acoustic generator, and I launch two disturbances, they're both going in the same direction, well, they're going to move at different speeds, right? The vortex is moving with the flow, the sound wave is moving at the speed of sound. But what it says is they don't interact with each other. So they don't modulate each other or perturb each other or distort each other. They're like two ships passing in the night. They're both doing their own thing. It also means, by the same law, it means that if I just excited a vortical disturbance, if I excited this convecting vorticity, it doesn't cause any fluctuations in acoustics or any fluctuations in entropy. And the same thing applies for any one of those three. So that moves me to the second bullet, which is just a restatement of what I just said. That these three modes are decoupled within the approximations of this analysis. So let's real quickly summarize those approximations. Linear, spatially homogeneous, no molecular transport. Those are the three major assumptions I've made. If I drop any one of those three, things start to change a little bit. So spatially homogeneous, so no variations in mean quantities. Linear, no molecular transport. And then this says what I just said. For example, velocity fluctuations induced by a vortical disturbance. We said vortical disturbances cause the flow to oscillate. Acoustic disturbances cause the flow to oscillate. But those velocity disturbances are actually independent of each other, and the one acts as if the other wasn't there. So you're measuring, when you take a hot wire probe or PIV, you're measuring the overall fluctuating velocity. But what this says is that within the linear approximation, there's actually sort of two canonical sources of those velocity fluctuations, which are totally independent of each other. Each of them is doing their own thing, and you're measuring the superposition of those. Finally, what this says is that there are no sources or sinks of these disturbance modes. So going back to those equations before, we had a convection equation equals 0, a wave equation equals 0, and a convection equation equals 0. So we haven't talked about how you create these disturbances yet, but once they're created, they just propagate with constant amplitude. They don't increase in amplitude, they don't decrease in amplitude. Again, I just want to emphasize within the approximations of this analysis, linear, spatially homogeneous, no molecular transport. Okay, let's make a few other comments. Acoustic disturbances, those propagate at the speed of sound. So sometimes you'll hear these called, you'll hear the term in the literature, you'll hear the word vorticity wave or entropy wave and acoustic wave. In reality, only the acoustic disturbance is a true wave, what I would call a true wave. The vorticity and the entropy disturbances are not waves. What's my definition of wave? I would define a wave as a disturbance that propagates energy without propagation of mass. That's kind of my informal definition. So for example, when I'm talking, there's energy that's propagating from my mouth to your ear. I'm not standing up and running over to you, moving air particles and putting them in front of your ear, right? It's the same as if when you play pool, right? If I put a whole bunch of billiard balls in a row, you hit the first ball, the last ball moves. But this ball didn't have to go all the way over there, right? So I didn't have to convect the mass over there to convect the energy. I mean, I didn't have to propagate the mass over there to propagate the energy. So that's what acoustic waves do. Energy is propagating without actually the mass moving. The same thing with ocean waves, when you have this big wave moving along, it's not that the water is moving necessarily with it. It's rather the disturbance that's moving. In contrast, an entropy disturbance and a vortical disturbance, the energy is being propagated by the convection of mass. That's what's causing the energy to move. Okay, well, all right, so let's think for a minute here about these two different velocity scales. One's moving with the speed of sound, the other is moving with the flow. So let's suppose I have let's think about length scales for a minute. Let's suppose I have a magic disturbance generator right here, all right? Let's suppose that it's a vortex generator, and every t time interval apart, capital T, that's not temperature, it's, let me put a squiggle through it. Every this time interval apart, I'm gonna pulse my vortex generator, I'm gonna generate an infinitesimal vortex, okay? So what's gonna happen is that I generate this vortex, it's gonna convect a distance u0 times t, then I'll generate another one. And a time t later, I'll have two vortices, right? And the distance between these two will be u0 times t, okay? And I can do this 1,000 times, and then I'd have 1,000 little vortices. I'd have this little wave train that was periodic. And so I can think about a, quote, wavelength of this vortical disturbance, which would be u0 times t. Now, now let's suppose that I was modulating this thing harmonically at a frequency f. T is equal to 1 over f, right? Where f is the frequency. So what that means is I can define a convective wavelength, lambda c, is equal to u0 divided by f, which I think I have on that slide. Yeah, so lambda is the wavelength, or in this case, the wavelength is the distance over which the disturbance repeats itself. The c denotes a convective, and it's u0 divided by f. Now, same thing, let's think about now this is a sound generator. It's generating a sound wave every t times apart. Well, that sound wave, let's suppose it's a low Mach number. Let's suppose the Mach number is 0.1. That sound wave is moving 10 times faster than the vortical disturbance is. So let me make circles to denote 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I generate a sound wave. In a time t, that sound wave will have moved this far. The next time t will have moved that far. It will have moved that far. So what's the observation? The acoustic the length scale over which the acoustic disturbance moves is a lot longer than the vortical disturbance, right? So the acoustic wavelength, which I've called this, is going to equal C naught divided by F. That's, and you've probably seen that formula before. So what that means is that, let's suppose I have a combustion instability, which is occurring at a frequency of 100 hertz. Okay, what that's going to do, as I'll talk about later, that's exciting acoustic disturbances, it's exciting vortical disturbances, it's exciting entropy disturbance, and they're all occurring at 100 hertz. But what's the length scale over which these disturbances are happening? Well, that's by those two equations. And what you can see is, if I take the ratio, which I have here, lambda of the convective disturbance over the acoustic disturbance, that's U naught over C naught, which is the Mach number. So in other words, if the Mach number is 0.1, the acoustic the acoustic length scale is going to be 10 times longer than the vortical or entropy length scale. So that's an important thing to keep in mind when we start thinking about how flames respond to disturbances, is that the acoustic and the entropy disturbance length scales are going to be a lot shorter than the acoustic length scale. In fact, a very, very important assumption, which I'm just going to briefly get into, is something called the acoustic compactness assumption, which says, which when it's true is a very powerful assumption. Basically, when the flame is short or small in size relative to the acoustic wavelength, that's called an acoustically compact flame. And in that case, it turns out that you can make some very significant approximations which are really powerful to simplify problems. And it turns out that in many cases that approximation is a good approximation. And it goes back to this thing, is that acoustic length scales are really long. So even as the vortical, you might have, you might see the flame getting rolled up multiple times along its length by a vortex. So clearly the vortical wavelength is going to be on the same order or even smaller than the size of your flame. The acoustic wavelength could still be much longer than the flame. All right, another observation. Acoustic disturbances are interesting because, like I said, they're true waves. So what's the big difference? What do waves do? Waves bounce off of things, right? Waves refract around things. Waves diffract through temperature gradients. So for example, when waves bounce off of things, what does that mean? That means when I'm talking, sound wave hits that wall, it bounces off, right? That doesn't happen with entropy and vortical disturbances. There's no analog to reflection. Similarly, refraction. So for example, if one of you needed to take your chair and go sit outside of the room and around the corner, as long as I talk loud enough, you'd be able to hear me, right? And you'd be able to hear me because the sound bends, refraction of sound. Now, if any of you are taking Professor Hansen's class on optical diagnostics, in many cases, if the wavelength is really small, you move into what's called the geometric optics or geometric wave limit. In that case, you only get along the line of sight, right? So if I took a flashlight and you sat around the corner, you wouldn't be able to see the flashlight because the light wouldn't bend around. But that's because the wavelength is really, 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 really small relative to the size of the door. But that's a good approximation for electromagnetic waves. Usually, acoustic waves are in the opposite limit, where everything diffracts, everything bends. In fact, if I turned around and faced the wall, you'd be able to hear me almost just as good as if I faced you, just because the sound is just wrapping around and bending around everything. And again, there's no analog to that for vortical or entropy disturbance. If I generate a vortical disturbance, the only way you're going to see it is if the flow carries it from me to you. If the flow doesn't, if the vortical disturbance, which is riding with the flow, if the flow is going somewhere else, if the flow is going that way, and you're over there, you're not going to see the vortical disturbance. In contrast, the acoustic wave, it's going everywhere, and you can see it. And in a similar way is the acoustic disturbances, as I referred to earlier, they're going upstream, right? Whereas the vortical and the entropy disturbances are they keep getting flushed downstream. And then lastly, this has important implications for the combustion instability problem, because again, you got all these disturbances, and when these disturbances are interacting with the flame's amplifying them, and it's generating lots of fluctuations in vorticity and entropy and sound. But these vortical entropy disturbances, they're actually just, they keep getting just spat out of the combustor. They're flushing out. Whereas the sound wave, when it hits the exit of your combustor, turns out the exit of a combustor is a really efficient reflector. Most of the energy just reflects right back. Very little bit of energy leaves the end of the system. And so that's why we have thermoacoustic instabilities as opposed to, you don't normally think about thermoentropy disturbances, thermoentropic instabilities. It's because you don't get the feedback. When you have acoustics, it goes, it hits something, it comes back. Yes, sir?
But you actually, so with the entropy waves, like as you have density gradients or spots that they come back through the nozzle where you have like flow acceleration, that generates pressure waves that then...
Yeah, you're absolutely right. So I was going to get to that later. So you're adding a very important caveat. So when you start relaxing some of the assumptions that I'm going to make, that in fact entropy disturbances, as they convect through a nozzle, when you accelerate an entropy disturbance, that does generate a pressure fluctuation which comes back. And that leads to something called an entropy mode. Absolutely correct. I was going to get to that. I was just trying, but you caught me oversimplifying things. I'm glad you're paying attention. But still, the general point is that the entropy mode goes away, but as the entropy mode washes out of the combustor, it actually generates an acoustic fluctuation which comes back in the example that was just mentioned. The key part of that, though, is you have to have a flow acceleration. If you just have an open end of a tube, the entropy disturbance just washes out. I'm going to go a little long, if that's okay with everybody. Sure it is. Because I just want to finish my point. I want to do an example. I want to think about, all right, we've talked about how you have these, well, let me jump ahead. Where's that dumb slide? Where'd it go? This slide summarizes everything we just talked about. So if all the math just shot over your head because you're sleepy or you're watching football, pay attention to this slide. Because what it says is, now I filled in all the X's. It says, okay, these are my physical manifestations, and this are these fundamental disturbance modes. How are these fundamental disturbance modes manifested? Well, the acoustic mode is manifested as fluctuations in pressure, velocity, temperature, and density. The entropy is manifested as fluctuations in density, temperature, and entropy. The vorticity by velocity and vorticity. So for example, if you look at something like velocity, now I just read it vertically, let's read it horizontally. So when you make a velocity measurement, you are actually looking at the superposition of an acoustic wave moving with the speed of sound and a vorticity wave moving with the flow. So if you just have a single point measurement, you have no way of differentiating between those. If you have a 2-point measurement, you can actually sleuth out what you have there, because you can do a cross correlation between the two and figure out, okay, actually 40% of that velocity fluctuation was a sound wave that was zinging by at the speed of sound, whereas 60% was a vortical disturbance just plodding by with the flow. Same thing happens with the density, but slightly differently. So if you have a fluctuation in density, so for example, you're making some sort of absorption measurement, what you're looking at is a superposition of, by the way, the temperature is the same, so let's talk about density and temperature at the same time. That is a superposition of an acoustic disturbance and an entropy disturbance. All right? So let me do an example here and then we'll take a break. So let's look at a real simple model problem. We said the unsteady velocity is a superposition of the acoustic mode and the vortical mode. Let's think about what would you actually measure if I had an acoustic disturbance which was oscillating harmonically and moving with the speed of sound. Okay, so this would represent an acoustic disturbance with an amplitude A lambda, and it's moving in the direction of positive x with the speed of sound c naught. So that's what this physically describes, a traveling wave with that amplitude. This right here, A omega, that's the amplitude of the vortical disturbance, and it's moving with the mean flow speed. So acoustic amplitude, vortical amplitude, moving with the speed of sound, moving with the flow. So just to keep things real nice and simple, let's assume that that the amplitudes of the two are equal. So I have an acoustic mode and a vortical mode, same amplitudes, all right? Now I can just use trigonometric identities and add those up, and this is what I'm going to get. So with a measurement in velocity that I would get would look like this, okay? And so what you can see is, if you're not used to looking at standing wave type expressions, I have a term here that's oscillating harmonically as omega t, and there's a phase shift at each, there's a phase difference at each different spatial locations x. But what's happening is so here's the harmonic oscillation. It's basically cosine omega t plus a phase. And then the amplitude of that velocity is given by this term, which is equal to 2 times a times this spatially dependent thing. Okay? So in other words, the velocity field's oscillating harmonically at each point as cosine omega t. Makes sense. But the amplitude of these oscillations are varying spatially like that. So let's just plot that up. Well, what I did here was I'm going to show you data as well. So this corresponds to a situation where the two don't have the same amplitude, but the acoustic mode is 60% of the vertical mode. Now, if you take this type of expression and you just plot what that looks like, if this is the unsteady velocity magnitude, so I'm not plotting the instantaneous velocity, but what I'm saying is the velocity is oscillating harmonically at omega t. What's the amplitude of that oscillation at each spatial position? It looks like that. That's the solid line.
So the U prime is U minus U bar?
Yeah. Yep. And this is amplitude. That's why I have the magnitude around it. Okay? So in other words, what that says is that at this point, it's oscillating with 8%. It's oscillating harmonically at omega t with 8% of the mean, whereas this location, it's 4% of the mean. But what's interesting is if you just measured the vortical disturbance, it has a constant amplitude in space, right? So in other words, if you go back to my expression, the amplitude of the vortical disturbance is just a omega, no spatial dependence. There's a phase that varies spatially, but it's a times cosine omega t plus a phase. Same with the acoustic disturbance. The acoustic disturbance does not have an amplitude that varies spatially. It's a times cosine omega t plus the phase. So if you only had an acoustic disturbance, you would measure a constant amplitude with space. If you only had a vortical disturbance, you'd have a constant amplitude that doesn't vary in space. You have a superposition of the two, and you get basically an interference pattern. So you've all seen interference patterns before. But what's happening is that the two are moving because they're moving at different phase speeds. At some points, they're in phase with each other. And so one's at amplitude A1, the other's at an amplitude of A2. If they're in phase, I'm going to see A1 plus A2. Now, at another point, they're going to be 180 degrees out of phase with each other because they're not moving at the same speed. There, the amplitude would be A1 minus A2. And so you basically set up a standing wave or an interference pattern. And we measure these all the time in combustion chambers when we have thermoacoustic instability. So let me jump back to a slide that I skipped over, this one right here. So this was some data taken by Jackie O'Connor. She's a professor at Penn State. And what she did was there's a flow is going left to right. So you have reactants coming out of this annular flow passage. This turns out to be a swirling flow. This is a cross section. And she introduced acoustic waves that were bouncing up and down. So what you have and what those also do is when they interact with the separating shear layers here, you excite a vortical disturbance. So what you have is an acoustic disturbance that really has no amplitude variation in this direction, and you have a vortical disturbance that's convecting in this direction. And when she went in with PIV and measured what's the amplitude of the velocity fluctuations here, or here, or here, or here, she got this behavior. Those are those measurements. And so initially when we looked at it, we said, what is going on? But quickly we put this together and realized, well, what we're looking at is we're measuring the velocity, but in reality the velocity is a superposition of these two canonical disturbances. Similarly, the phase, if you look at the phase, if you only have the vortical part, it would look like this as a function of distance. Only acoustics, it looks like that, but the measurement looks like that. And that's very simple, very, very simple model problem really nails it. Okay. Tell you what, I'm just really going to impinge on your time because I have so much to say. I want to, in one slide, talk about what happens if I relax all those assumptions now, okay? So remember we said we assume linearity, we assume a homogeneous flow field, etc. And within those approximations, the equations that were sourceless, so the amplitudes, once you excite them, don't change in space. They stay constant. They just convect or propagate with the sound wave. They're also independent of each other. Now, those modes will start to couple with each other, but also change their amplitudes when you start including some things. So first of all, boundaries. You have a question? Okay, so boundaries. So think about it. If I have a sound wave impinging on a wall, well, it may be that in the domain, the acoustic and the vortical disturbance are independent of each other, but at the wall, you don't apply the no penetration boundary condition separately to each mode, right? The unsteady velocity normal to that wall is 0. The unsteady velocity tangent to that wall is 0. And so what happens is those modes actually couple with each other because at the wall, U1 omega plus U1 or 1 lambda, whatever, it's equal to 0. So for example, no vorticity at the wall right now. If I take well, as I'm talking, that sound bounces off that wall, and at the wall, the velocity's got to be 0. So what that does is the sound wave actually is exciting a vortical boundary layer at that wall right there because of the sound wave hitting it. So the modes are coupling at the wall. And so and how does this manifest itself? Well, we call that acoustic damping. You may have heard of acoustic damping at boundaries, but really what's happening is energy is moving around between different modes. So overall, the energy is conserved in the disturbances, but the energy is moving from the acoustic wave, which is moving with the speed of sound, to the vortical wave. So what that wall does is it provides a mechanism whereby a disturbance that propagates with the speed of sound, is compressible, and is irrotational, can pump a little bit of energy into a disturbance that moves with the flow, that is rotational and is incompressible. In the domain, there's no way those two modes can match with each other subject to the linearity and homogeneity approximation. But at the wall, there's a mechanism for that to happen. And so what happens is the acoustic wave, when it reflects off that wall, it reflects with a slightly smaller amplitude than it started from, because some of its energy went into a vortical disturbance. Same reason some of its energy will go into an entropy disturbance. Okay, so that's one effect, boundaries. The next is regions of flow inhomogeneity. So now let's think about what happens if we relax this assumption that there's no spatial variations in mean pressure or mean density or things like that. Well, it turns out that when, for example, a sound wave propagates through a temperature gradient, it generates vorticity. So the modes start to couple with each other. This is the comment that was just made. When you take an entropy disturbance and you run it through a region of inhomogeneous velocity, i.e. you accelerate it, you generate an acoustic wave. That was the comment that was just made, that when you take an entropy disturbance and you run it through a nozzle, you actually generate an acoustic wave. So the two modes couple. And there's a whole bunch of other examples. But in regions of flow inhomogeneity, all the modes start talking to each other and interacting with each other. And then finally, there's nonlinearity. I just gave the example of vortical disturbances, that when you have a vortex, remember I said, why is the pressure fluctuation 0? Hold on, we all know that vortical disturbances, that vorticity creates pressure disturbances. Well, that's a nonlinear effect. So to second order, the vortical disturbance excites pressure disturbances. And so that's actually how jet noise gets generated. If you've ever wondered why a high velocity jet like an aircraft engine generates sound, it's through a nonlinear mechanism whereby you have these vortical, basically have these turbulent vortical disturbances, and basically because of nonlinearities, a little bit of the energy in those turbulent vortical disturbances gets transferred into the acoustic mode, and the acoustic mode propagates away at the speed of sound. The vortical disturbances just convect with the flow. And all of this stuff is happening in combustion systems, all right? You have sound waves getting generated by the flames, they're bouncing off of walls. When the sound waves interact with the flame, they generate vorticity and entropy because of this effect. And then those vorticity and entropy modes, then they convect downstream. When you have an entropy disturbance or a vortical disturbance, they interact with the flame, they generate sound. And so all the modes basically get mixed and jumbled and matched and moved around when you propagate through the flames. But then once you're downstream of the flame, it's kind of homogeneous. And then then you can kind of use the assumption, the analysis that we used to this point. But then when you hit the nozzle, assumptions break down. They start talking to each other and interacting with each other again. Okay, does anyone have any questions? Let's take a break. It's 3:15. We'll go till 3:30. Actually, let's go till 325. All right? 325.